Hi, during this video clip we are going to cover the first session about neural networks. So let's go to my full desktop. So neural networks is a methodology or forecasting technique that emulates the brain. So the brain has capacity to assess data that is probably not very accurate, it's not very clear. And that is the aim of this method. Previously, we have covered during these sessions methods that are designed for cross-sectional data. So, and that are used as well for forecasting time series. These methods are linear regression. Yes, so as you can see here, this is the equation for linear regression. We can add logarithmics to linear regression to the variables, and we can also add R autocorrelation, like lag variables to our specification. And apart from lag variables, we can also use external information. So as you can see, set here denotes variables that are external, different from the variable that we want to calculate. Also, we have covered logistic regression. Logistic regression is as well a special case of these cross-sectional methods designed for cross-sectional data and that are used for forecasting time series. The idea of logistic regression that we covered during the previous session was to predict binary outcomes or binary variables. A binary variable is a variable that takes the number or returns the numbers 1 and 0. 1, for instance, when it's time to buy, and 0 otherwise. 1, another example can be is 1 when we want to forecast a day that is not raining. Yes, 1, and 0 when it's raining. When we have a forecast that that date is going to rain. So as you can see, we can use as well this. So among data mining algorithms for predicting cross-sectional data, so we have neural nets. Neural nets are very popular for forecasting a time series. So here we can see how at the beginning we have different types of stages here on this graph. On the first circle, on this column, we have the variables, all the variables. Following that, we have another layer. They are called layers, actually, these columns, yes. And in this layer, the computer is going to try to find different type of mathematical calculations to calculate this circle that we are going to call nodes. So as you can see, even these calculations, the calculations or the interactions between these variables that come here to this node, they cannot even have any meaning. The only thing that we want to do to make sure is that these nodes are going to make sense to calculate the time taken to break even, yes, or retail sales, yes. So through the interaction of these nodes, yes, we are able then to assess data that appears to be very complex. And this is the way in which a neuron in our brain works. So our brain actually uses neurons that provide complex computations among these variables in order to assess what are going to be the outcomes nodes for our or the results for our forecasts in our brain. So we have that neural nets forecasting. We have for as an example for this type of method or estimation technique. We have applications in all areas of the science, really, in physics, in anything that you can think. There are applications of this. Particularly powerful neural nets are for finance and economics as well. So you may find papers using neural nets to forecast shares, forex, bonds, etc. So in general, we have mixed results compared to other methods, yes, and seem to work best with high frequency data. High frequency data is data that has like a short span of time. An example of high frequency data can be data in days, even data in hours, in different type of hours, can be in 4 hours, in 1 hour, even data in minutes, yes, 15 minutes, 30 minutes, 5 minutes, and even very high frequency data that is tick data. That means that real-time data. Yes, so for instance, in Forex, you can see that we can download tick data, and obviously that is going to give like the highest frequency for any data. We have here as well examples for the renewable energy. We want to measure, for instance, what is the efficiency of different types of ways to produce renewable energy, and that is something else that neural networks can forecast. So neural nets have been very popular in the 90s and 2000s. So the previous methods that we cover here are methods that have been in place for sometimes 50 years or more, 60 years, 100 years. In the case of the Winter-Holtz method, it has as well a lot of so this method, actually, neural nets, is probably one of the most advanced methods, but however, I would like to say that it has been popular like 20 years ago. So, but I believe that this is going to help you to go beyond and find more forecasting techniques. And I hope that my module is going to allow you to understand, like in a very practical way, how to use R in order to learn new forecasting techniques. And in doing that, I think you will be ready to make a master or a doctorate, or as well you will be able to work in like a financial firm as an analyst to forecast something, or in any business to forecast any of the time series in any sector of the economy, the health sector or the government sector, whatever it is. So the main idea then that I want you to understand from this session is that neural networks capture a complex relationship between outputs and inputs by creating layers of derived variables. So y is the output variable. We saw an example before, a graph. X are the original input variables. That was the first column in our previous neural nets scheme. And we have this g of x, this function, which are derived input variables. So which derived variables did we see in linear regression for forecasting? So we can see how here we have a function of the function of the function of the function of x, right? And I think that is the way in which we derive variables, yes, here in neural networks. So from the previous graph, I say that these circles are called nodes. So these are the input variables, yes, and this is called as well the input layer. This is the hidden layer. So in the hidden layer, we have the derivatives of our variables and the interaction between variables. In this case, we have a layer of size 3, yes. And finally, we have an output layer, which is y. In our previous example, the output variable is y here. So in doing that, we are going to capture the relationship between these two variables in this hidden layer through derivatives, yes, and as we control for the weights that we are going to give to every derivative, we will be able to arrive to the best outcome possible here in the last output layer. So in this example, we have a single hidden layer, but in the reality, you can add even more like hidden layers to your analysis using neural networks. So the output layer from one layer is input into the next layer. So the output node, and this is the way that probably like the rationale in which neural networks work, is that the output node, yes, this output node j equals the function or the activation function, yes. Generally, we have functions that are linear, exponential, or S-shaped. In R, you will see that this is automatic. It finds the best function, activation function. We use a bias, yes, that controls for the contribution of node J, yes. And we have different weights that we are going to give to every explanatory variable. So here you can see actually in the reality how it works. So initially we have this node 1 and this node 2. There are two variables, yes. And through the activation function, we are going to give them certain weights, yes. Say from 1 to 100, right? From 0 to 100, they will have weights, yes, of interaction, yes. And these weights are actually the weights that are going to be calculated using neural networks. In our previous models, what we were trying to calculate were the coefficients. This time we are calculating not the coefficients, betas, but the weights. And obviously there is not a rational for it. It's just iteration. Iteration means that is like by means, we find these weights by means of simple random cases. So we try to iterate up until we converge to the best solution. Finally, you can see here that we have a bias, yes, which is this variable theta, right? And this bias is going to control the contribution for each hidden layer, provided that we have these weights, yes. And finally, you can see that after we calculate these contributions, we again give certain weight to these nodes in order to arrive to an answer here for our output layer. So here I have an example of this neural networks. We have here the observation 1 to 6. We have here the FAT score from 2 to 4, 0.2 to 0.4. The SALT score, yes, and the acceptance of cheese, yes. So we have different FAT scores and SALT scores, and a final variable that is the acceptance of cheese. So we want to know what is the acceptance of consumer cheese provided these FAT scores and SALT scores. What is the favorite? So in the input layer, we will have in 1 the FAT score, and in the node 2, we are going to have SALT, the SALT score. Again, through the function, yes, we are going to calculate these weights, yes. The algorithm calculate these weights. I think you will not need to calculate anything, but this is how it works, yes. And finally, theta will be calculated for each of these hidden layer nodes. The values probably really will not mean much to us. It will be like some power that we are going to give to these nodes, and these nodes are going to be weighted one more time in order to get to know what is the consumer acceptance in the final output layer. So the circles then represents the nodes. W on the arrows are the weights, and theta are the node bias values. So here we have then another example. We carry on with the same example. We have, for instance, here that in practice we have that a FAT was 0.2, coming from this example, 0.2 and 0.9, yes, 0.2 and 0.9. Then we calculate the weights using that function that we saw at the beginning, and this is going to give us theta here. Having having calculated the theta, we are going to be able to give new weights here for these hidden layers, yes. These are like the powers of every node, and finally we will be able to arrive to the question that at this level, so therefore we have a 0.506 result using the two first scores for fat and salt, yes. The way in which we classify is by means of like setting a threshold for this result. So if our result is higher than 0.5, we can classify our acceptance as 1, otherwise it will be 0. So computing this figure then shows how computing nodes outputs in a boldface type using the first observation in the tiny example and a logistic function. Okay guys, so here you have then the logistic function to calculate the 0.43, and here you have the function as well to calculate the last layer, which is 0.5006. So here we use the logistic regression in order to calculate the nodes that we want to assess. In the reality, you can carry on adding more layers in R. It will be very easy in the notation in R. You can set layers to 1 or 2. But the most popular in forecasting is the single hidden layer. There are many reasons for that. One of them is that sometimes we can overfit our data when using more layers. And also, every time that we like add more layers, we will add more complexity to our analysis. So here we have then an example one, which is a neural networks with no hidden layers. G is the activation function, is a linear activation function. So as you can see here from this, with no hidden layers, this neural network is looking like linear regression. So here you can see that actually neural networks, for the neural networks, in order to produce something different from a linear regression, we need to have a hidden layer that is going to calculate the very complex relationships between variables. This is the hidden layer for a log or an exponential activation function, yes. No hidden layers again, but here you can see that with no hidden layers, we can also use logarithms in order to calculate the same things. We covered this topic of logarithm before when we try to smooth our time series. So we covered as well these sigmoidal activation functions before when we use logistic regression. So here we have the logistic function, as you can see. And the logistic function is very interesting because it allows us to classify variables in no. For instance, let's say that this is no, this segment, and this is yes, right? So it's example the same. We have here two functions that are going to help us as well to classify variables in yes and no, buy and sell, recession or no recession. Here we have the logit activation function, yes, for logistic regression. So as you can see, using neural networks and no layers, we will be able as well to run a logit or a binary outcome regression, yes. And this is how it looks when we try to estimate that using neural networks. So we can also have an architecture for roll forward forecasting, and but I think I will stop here my lecture. Right. During my next video, I will explain more about neural networks. Here we have the input layer, the hidden layer, and the output layer. In this case, we have several roll forward forecasts. Yes, so as you can see, the input layer contains the same variable in lags, and the output layer contains our forecast for the future. And I want to finish this session by saying that this is the structure or the architecture that we are going to use for our sessions.